in the one obvious room with Xin. Xin, how are you?
I'm good, Katie. How are you?
I'm great. I am so looking forward to this talk. Xin is a machine learning engineer at Eliza, and her talk is Getting Over the Boring Stuff Quicker, Automating a Semi-Automated Speech Audio Annotation Tool. I'm going to watch this one. Take it away.
Thanks, Katie. Hello, everyone. I'm Shane, as Katie mentioned. I engineer machine learning, and today I'm going to talk about how I built a semi-automated speech and audio annotation tool so that I could get over the boring stuff quicker, aka data labeling. But first of all, let me introduce you to a corner of my life. So I have an English-speaking partner and a Chinese-speaking parent. So their communication channel is through me. So if my partner wants to talk to my parents, he has to go through me and vice versa. I am the translator. At the beginning, it sounds fun to be a translator, but after a little while, it can get really tiring, especially for long conversation. So what I want is for my partner to communicate with my parent directly. And I happen to be able to code. So I thought maybe I could build something for them to communicate with each other directly in both physical world as well as in the virtual world. So I know that in order to build this little application, I will need two main components. The first one is speech recognition to turn the audio speech into text, and then I could do a language translation on the text. For translation, I found some good open source library to do so, and actually to perform a pretty decent job. So my main focus would be speech recognition. So what is speech recognition? It is a technique to enable recognition or translation of human speech into text via computers. In another word, is to convert audio speech into text. And I found some good open source deep learning model to help me to do this job. And one of them is the deep speech model developed by Mozilla. So what is deep speech? According to the paper, the deep speech scaling up end-to-end speech recognition, the core of the deep speech system is a recurrent neural network, RNN, trained to ingest speech spectrograms and generate English text transcription. So in their system, they have this recurrent neural network, which is really good at handling input data in sequence because they have some kind of mechanism to keep the memory of the sequential data as the input. But I won't go to the details of this neural network in this talk. And the input of this system is a spectrogram, which is an image representation of the frequency, time series, and the amplitude of the audio signal. So the reason I chose deep speech is that it provides an end-to-end deep learning speech recognition model. So it doesn't need a phoneme dictionary or doesn't even have a concept of phoneme, which simplify the annotation process of training data a lot because I don't need to map the phoneme into each word or into each syllable of the word. So all it does is it takes the audio clips as the input to this model system, and it converts it into the spectrograms and then feed the spectrograms into the neural network for training. So I was super excited about this model, and I was very excited to try out the pre-trained model released by Mozilla. And here's the result. When my partner said, it is cold here, even though it is summer, well, we are in Melbourne, the deep speech model performs pretty well. It captures all the meanings of the speech. But when I said the same sentence, it became cold here, even though it's somewhere. Well, it sounds similar, but it didn't quite get all the meanings from the speech. And I thought my English was okay, and obviously deep speech doesn't think so. So in order to make the speech-to-text model more robust, especially with speech such as English speech with accent more robust, I will have to fine-tune the current pre-trained model with some speech of variations. So to fine-tune the deep speech model, I know that I will need some audio clips, and then the model would convert those clips into spectrograms. And I also need the transcription or the annotation of those audio clips as like the ground truth data or label data. Then I could feed all of both of them into the recurrent neural network or the deep speech model for training. Great. So I know that what I want to achieve is some like cool magic speech recognition, and I have also identified a deep learning model to help me to achieve the cool magic, which is the deep speech model. And all I need right now to achieve my magic is the data, especially the labeled or annotated data for the audio clips. As we all know, that's the field of deep learning and machine learning. So that's when speech audio annotation comes into the picture. There are many ways to do speech audio annotation. One of them is a manual annotation process. So I sit there, listen to many audio clips, and then manually write the transcription or the annotation data into, say, a CSV file. This can be really time consuming and soul crushing. So or the other way is that I can automate or semi-automate this annotation process by leveraging the pre-trained model inference, as well as some of the existing speech recognition servers, such as the Google speech-to-text API, to do prediction on or the transcription on the audio clips automatically. And all I need to do is to sit there and then check the correction of the result and do minor changes if they are not 100% correct. In this way, I would hope that I could significantly cut down the annotation time because I don't need to do the transcription from scratch. I just need to potentially do some minor changes. To further speed up the process, in addition to using the speech recognition service as well as the pre-trained model inference, I could also fine-tune the model periodically after collecting a fair amount of annotation data to improve the model accuracy for customized data set. In my case, it would be English speech with accent. This way, the future prediction or inference of the updated model will be more accurate. As a result, I could spend less time to do the minor correction, therefore, to speed up the annotation process. And this inference, training, inference feedback loop is the essential workflow of a semi-automated annotation system. Now, I know what I want to build. It is a semi-automated speech annotation tool. And the next thing is, how do I build it? So here is the system diagram of the tool that I designed. There are mainly two parts. The first is the front end as the user interface coded in React framework. So that's this component is for the user to upload audio clips and to do transcription, annotation, etc. And then I also have a backend system, which is written in Python using Flask, the framework, to host all the core components. For example, the recognition to call the existing recognition service, model inference, the training data annotation, as well as the model training component. So let's zoom into the backend system and see what the annotation workflow is in detail. So when the user uploads an audio file, the system or the tool would segment the audio files into smaller chunks using a technology called VAD, Voice Activity Detection. It is a detection of the absence or presence of human speech in speech processing. Essentially, what it does is to segment the audio file into smaller chunks, which all contain active human voice, and to get rid of the noise, silence, or pause in the audio signal. And then we will perform inference, model inference from the pre-trained model on those audio segments to get the transcription Then I will check whether the inference confidence is higher than a predefined threshold. If it is, then I would just use the inference result as the annotation for that audio segment. If not, then I will see whether I should run the speech recognition service. If it does, then I will use that results from the recognition service as the annotation data for that audio segment. While if we don't run it, then we will have to do a manual annotation. And this is the workflow without the training component. Now, if I want to add the model training component into the workflow, it looks like this. So essentially, for the model training, I just need to collect all the annotation data from the audio segment and then feed them as the input data to train a fine-tuned model. And once the training is finished, then it would generate a new model file, and the backend system is actually monitoring that model file. As soon as it gets updated, the backend would actually get triggered a graceful reload to take that new model file into effect for the future inference of the audio segment, which means the inference for those audio segments in the future would have a better result theoretically because it used the updated model file. So in order to package the system into one package so that I could deploy it in a different environment, for example, in cloud environment, and also for my own learning purpose, I decided to containerize all the components and orchestrate the components using Kubernetes into one deployment package. And here is the diagram of the deployment package. So I have a front-end container, and I have a back-end container. And I also have a persistent volume component to persist the output of the system. For example, the audio clips, the annotated data, as well as the fine-tuned or updated model. And I use Kubernetes to orchestrate all these components into one deployment package. And I'm going to show you a screen record of the demo of this tool. So you can see this is the UI of the tool, and I have a project configuration settings on the top, and also a place for the user to upload the files. So I have a test audio file in WAV format. So if I upload it, it would generate an annotation table down here, and we can see the 2 audio clips here and in one page. In the table, there's audio columns to host audio clips, annotation columns to have the text box for the manual transcription, and the deep speech column to actually show the result of the deep speech model for the particular audio clips and its related confidence of the inference. And I also have a Google speech-to-text column, which is not enabled at the moment. And then the last column is to annotate the data for particular audio clips and then save those data in the persistent volume when the button is clicked. Now, I'm going to play the first audio clips.
It is cold here, even though it is summer.
And as you can see, that's the deep speech result is pretty good. It's cold here, even though it's summer. So it captures everything from the audio clips. Now I'm going to play the second clip.
It's cold here, even though it's summer.
So it's me saying the same sentence, but the deep speech didn't quite understand. So it became cold here, even though it's summer. It kind of lost the meaning of the speech a little bit. And as you can see, the confidence for the first clip is higher than the confidence of the second one. Now, if we go to the project configurations, what we can do here is that we could set the project name. The project is like the annotation project name. I'm going to put it as PyCon-demo, and I could also configure the model confidence threshold. It really depends on the pre-trained model. And here, I'm just going to put a number that is kind of like correlated to the inference result. It's -40. And as you can see, because the first audio clip has a results confidence is high as -30, which is higher than the threshold. So the deep speech result is actually copied to the annotation text box automatically. But for the second one, the confidence -45 is lower than the threshold. So there's no result or anything get copied to the annotation text box. And at this point, the Google speech to text is still not enabled, but we could enable it up in the project configurations panel. So what it does once it's enabled is that at the backend, it will actually have a request to the Google speech-to-text API for a particular audio clip, and then get the transcription result back. And as you can see, well, the first clip, it gets the result. It's pretty good. It is called here, even though it is summer, which matches the deep speech result. And for the second one, you can see it is called hair, even though it is summer. It's slightly better than a deep speech result, but still not quite correct. But in this case, I set it so that the result of the speech-to-text API is actually copied to the annotation text box. And in this case, I just need to do some manual small correction to correct the annotation result. So that before I hit the save button to save those annotation data, I want to show you where those data is saved in the backend. So here, as I mentioned before, that I have a persistent volume in my deployment package, and I set it to the path is /data/models on the host. Host in this context is a VM running on my local machine where this cluster or the Kubernetes cluster is running. So if I go to the VM, go to /data/models, then let's have a look, see what's inside this path right now. And you can see there's two folders here. They are clips and trained models, and they are actually generated on the system spinner to hold some of the output of the system. Now, if we go back to the UI of the tool, and then we hit the save button to save the annotation data into the persistent volume, and now we can see there's a new file here, it's pycon-demo.tsv, and pycon-demo is the project name of this annotation exercise. And inside the file, you can see the two clips, the names of the clips, as well as the transcription of each audio clip. And it matches the one that is actually from the UI tool. Now, I also have a setting here to automate the annotation. So what it does is that if the audio, if the inference result or the transcription is higher than the, it has like the confidence higher than the threshold, or if the Google speech-to-text API is enabled, then it would take the result of either of those two settings and automatically save the results back into the persistent volume without human intervention. And I do a demonstration here. Once I enabled it, and I also set the project name to pycon-demo-auto to distinguish it from the previous annotation file or annotation data. Now I enable these the annotation automation settings, so that I don't need to do the manual human transcription, or I don't need to click the save button to save those data. I would just take the results that is generated by either the deep speech model or, for the first one, or the Google speech-to-text for the second one. And now you can see at the persistent volume, I have a new file, pycon-demo-auto. And inside the file, you can see there's two same audio clips names, and then we have the transcription for each of them. As you can see, for the second audio clips, the transcription is different from the one that in the previous file, because this one is actually the result from the Google speech-to-text API. Most of the time, I think this setting is a little bit risky, especially when I don't have confidence in either of the service, or like the recognition service or the pre-trained model. I would like to actually double check before saving the data to make sure that the training data has good quality to train a high accuracy model. So I disable the settings and revert the project name back to PyCon demo. And now if I want to train the model with the annotation data, I could do some settings here. The first one is model training epoch. I could set it to 1. The second one is training learning rate. If I set it to 0.0001. And then I could trigger the model training or fine-tuning just by clicking this button here. And what it does is actually trigger the training process in the backend. Now, if we go back to the log of the backend server, which is Kubernetes pod, and let's have a look whether the training job or how the training job is triggered. As you can see in the log, there are lots of information here, but we find the information that we want is these 2 lines. So the first one is transform training data succeed is true. So when the training is triggered, the backends actually need to convert those annotation data that we collected into a compatible format for deep speech to perform a training. And what it does is actually split the training data into 3 sub-data sets: the def, test, and train. And as you can see here, I have a def.tsv, a test.tsv, and a train.tsv, 3 data sets for training, evaluation, and validation for training. And the second line shows that it's a start model training for 1 epoch with learning rate 0.0001, which are the settings I put in the UI tool. And if I scroll down here, you can see that the training process is triggered and the checkpoint of the pre-trained model is loaded into the process. And a new kind of like fine-tune or training iteration started down here. And once the training process is finished, it will generate a new model file, and which is monitored by the backend server. So as soon as that file is updated, the backend server will actually trigger the graceful reload, take that file into effect for future inference, which hopefully would have like a more accurate result for a customized data set than the pre-trained model. So that is the demo of this semi-automated annotation, audio annotation tool. And through the building process, I learned a few things and have some takeaway that I would like to share with you all. So here are some takeaways that I summarized. The first one is there's a pattern for setting up a inference, training, inference, feedback loop of machine learning model to improve the model performance over time by combining the inference and the data labeling process together. And the second point is that a standard machine learning pipeline can be established on top of this pattern. Is this inference, training, inference, feedback loop pattern, including components of the data processing. In my tool is the annotation process, and then the model training as well as the model inference. Also, the orchestration of a containerized component in such a pipeline provides improved modularity. So I have different components serve different purposes. For example, in my case, I have the backend and then, the front end, the backend, and also the recognition or training, annotation, and inference components. And also, it can improve the reproducibility so that I actually package the system into one deployment package, and so that I could deploy into different environments, whether it's on the cloud or on my local computer. And it has everything in it, all the dependencies needed inside this one package. And the last thing is it could actually improve scalability, especially using a container orchestrator like Kubernetes. You could actually configure whether you want to auto-scale a particular component based on, for example, data volume or the request load. And this is the overview of the tool that I built to do semi-automated audio annotation tool. Thank you very much.
That was so wonderful. Thank you for that, Xin.
Thank you, Katie.
You had a 10-minute video demo and it looked like you were doing it live. That was so well rehearsed. Oh, that was so good.
Thank you.
If any of our attendees have questions, you're happy to answer them over in the hallway?
Yes, definitely.
Wonderful. Well, we are now at lunchtime, so we have a whole hour where we can all get up and have a stretch, and we'll see you back here in an hour.